area between curves. So the main thing when we started talking about integrals was area, right? When we very first started chapter 5, integrals meant area. This little S-shaped thing, weird looking symbol, which we now know is kind of like an S for sum, from a sigma kind of a thing. But you know, this meant this area under curve. We talked about why we might need it. We talked about rate and distance, and then of course we figured out the whole antiderivative component, which of course brings in all these things. So we've used integral for stuff that wasn't area also, right? Think about the packets. We set up an integral every time we want to go from a rate, like gallons per hour, to gallons, you know, like we did on that problem with the sand. You know, so the integral can be a lot of things that don't have anything to do with area. Okay, now we brought it back to meaning area here again. Oh, the average value function, that was in one of those homework problems, right? We used it for that. Remember, average value of a function from this point to this point, you do the integral divided by b minus a, right? An average value formula. So we have that use of it. But now we come back and we use area, and then we're gonna, the new thing we do today, the other thing that's in this section doesn't have anything to do with area again. And so that's kind of the fun part of chapter 7, kind of like when we did derivatives. We had this slope idea, rate of change, and all the different uses we had of it with max and mins and related rates and all those kind of things. Same thing with this idea of integral and all the different application things. I mean, that's why calculus is kind of a big deal, kind of like algebra. You know, algebra is a big deal, just it's mostly notation, but it's using variables to stand for unknown quantities, and all the things you do with algebra makes it kind of a big deal to learn. You know, there's a lot of just individual little topics in math that are just that, these little individual isolated things. But the things that have wide-ranging uses are the ones that you know, like algebra and that calculus, same thing. Anyway, what I've done here, I know I told you not to do parts B and C, not to spend time with that, but you were supposed to do, the problem in part 1 and 2 was it midpoint or left? What did it say?
Part number 2 is
midpoint. 2 was midpoint, so 1 was left.
Yeah.
Okay, so if you were going to do 5 left rectangles from 0 to 1, they would be 0.2 wide, so I've just divided that up here a little bit. So if we were to have done this on this problem, it would look like something like this, right? I mean, if we were doing that, it's not that it was difficult to do. It's just that's not our emphasis right now. But the first left would be right here, and it'd be 0, and then the next left rectangle would be right here, and that's what they would look like. I mean, that's what it's kind of strange looking, but that's what a left rectangle would look like when you're doing a region between two curves. You would take the left end of the interval, put it into the top function, put it into the bottom function. That'd be the height. You would subtract, right? You would subtract, and so what you saw me do here, I just wrote that. So right here, this would be f. F is the top graph, so f of 0.2 minus g of 0.2. That would be this height right here. And then times your width, which I pulled out in front over here. Okay, so anyway, that's what 5 left rectangles would look like, approximating that area. Okay, and so that was what parts B and C were about. But as far as what you were supposed to do was simply set up your integral 0 to 1. We were doing vertical strips. I don't think it said how you had to do it, did it? It just said to find it. And what was this top curve? What was the top curve on that one? Square root of x, so x to the 1/2 minus, was that x squared? Right? That's it. I mean, that's how we do it. We think of this as a skinny little rectangle, right? Think of, we call it a strip now, but it's basically a skinny little rectangle because we want to think of adding up an infinite number of these rectangles. So it's just like adding these up. The ones we're going to add up are going to go from 0 to 1, so that's where we get this. The height of the little rectangles is going to be this y value, x to the 1/2. Remember, what is that y value? It's x to the 1/2. What is this y value on this graph? X squared. So it's this y value, x to the 1/2, minus this y value, and then times the width of those little teeny strips, which would be the dx piece. Okay. Now, they did say, and I told you not to, I think, I thought I said this, you don't, it said find the answer by the FTC, right? Exactly, kind of thing. Well, if our quiz, I put this in the no calculator part, then that's what I'd want to see. Or maybe if I put it in the calculator part and I said that, I would want you to do your antiderivative. So I'd want you to do this, raise that up to 3 halves, divide by 3 halves, minus 1/3 x cubed, 0 to 1, and I'd want you to actually do this. Okay, you plug a 1 in here, 1 to that is just 1, so that'd be 2/3. Put a 1 in here, but if you just typed in your calculator, I'm fine with that today. Okay, minus, and you put a 0 into both of those, it'd just be 0. So that'd be 2/3 minus 1/3 is 1/3. Is that what you got for that one? I feel like that's not right. Is my drawing wrong?
It's just X.
Oh, no. I told you wrong. It's not the square root of X.
Well, but my graph looks like square root of X. It doesn't look like it.
Your other picture was right.
Yeah, that.
Well, that picture's right. What in the world is that picture?
There's a different problem like that,
There is?
I think. Either that or it might have been the example you gave us yesterday.
Oh, that was X to the 1/3. Yeah, yes. Oh, maybe that. That's weird. Was there one?
There might have been one, it might have been like 17.
I drew it yesterday.
There's something that's similar to it.
Kind of looks
I
like
feel
that.
like I've seen it.
Yeah. Well, yeah, because yesterday we had X to the 1/3, which would look like that one. They're very similar. Cube root and square root are very similar in the first quadrant anyway. Well, anyway, there you go. That was good practice. I had fun doing it. But that would be the idea. You're right. If this was just X, then that'd be easier. This would be 1/2 X to X squared, right? So then when we put a 1 in there, this would have been 1/2 instead. So 1/2 minus 1/3, that'd be 3/6 minus 2/6, which would have been 1/6, right? So we still want to have that capability to be able to do antiderivatives by hand and be able to do the fundamental theorem, right bracket notation, f of b minus f of a, right? We still need to be able to do that. On the packets, you're going to have some no calculator ones where that's in there. Our quiz, probably, the next quiz we do is probably going to be all calculator. So most of the problems we do, I will, it'll just be set up your integral, put it in your calculator, get the answer most of the time. Our focus right now is setting up the proper integrals. Okay, it never hurts though to do them by hand, on some simple ones just for practice, but you'll get some of that in the packets. Okay, all right. So number 2 was this. What do we have? Sine and cosine, and it was from 1 to 3. I better double check with you. I'm on a roll here. Make sure I did this right. Okay, and I've drawn in some midpoint rectangles just to show you what this would look like. Okay, so again, we would divide it into, what was it, 4 subdivisions this time? Were you supposed, or was it, how many was it? 5, must be 5 again. So between 1 and 3, so here's 1.5, 2, 2.5, and 3, and then I went in the midpoint of those. So again, you would just find the midpoint of that subinterval on that curve, the midpoint of that subinterval, and you would draw in your rectangle. That's what midpoint rectangles would look like in a region like that, okay? And then I just went to the different midpoints, subtracted the y values, and then times the width, and that gives you the area of each of those, okay? So that's what it would look like. But if we're just doing the problem, everywhere you draw a strip in this region, and that's the key, you have to think from left to right, will every strip touch the same curve on the top and bottom? In this case, it does, right? And so it's going to be what, the sine curve on top? So it's going to be sine x minus cosine x dx, and then it goes from 1 to 3. That's it, right? And then go to your calculator. What was the 2.2306, 2.231? The 3 decimal places. Okay, so this problem we talked about yesterday, we did it the way we did it with a horizontal strip. This one would be better done with a horizontal strip if you had that option, but you were not supposed to do that. You were supposed to, they broke it up into 3 pieces like we talked about. The horizontal strips would be better because every horizontal strip you draw in here is going to touch the line on the right, and it's going to touch the parabola on the left. And so just to review that, so we set up What's this x coordinate right here?
Um,
What's this x coordinate?
X, Y, or X minus 2.
No. Y plus 2. It's a little strange, right? If I ask for the x coordinate, you're giving me an answer that's got y's in it, aren't you? Right? What is this x coordinate? It says right here what x is. It says x is y plus 2, right? Isn't is mean equals, right? X is y plus 2. So every x on this is y plus 2, right? That's what you want to think of. So every x on this line is y plus 2. So it's going to be that x minus, what's that x? 1 minus y squared. Every x on the parabola is 1 minus y squared. So we're going to subtract that. And then the dy, and then those strips, and I always say this to myself, to get this part, for almost every application we do throughout chapter 7, this way of thinking is helpful. The strips fill the space from where to where? Well, the strips fill the space from -1 down here to 1 up here. -1 to 1, because there gets to be some confusion. Are we doing x values or y values there? Well, first of all, we're doing y's in here, so they better be y's on our integral anyway. But I think you just think the strips fill the space from -1 to 1. Okay, so we did that yesterday. But what you were supposed to do is divide this into 3 pieces. You were supposed to do this piece, you were supposed to do this piece, and then this triangular piece. So what's this y value right here? No? What's this y value right here? No? It's 1, right? It says it right here. What is y? Y is 1. Every point along here, y is 1. Doesn't have an x in it. That's okay, because it's the same every time. So y is 1. Minus this y value. What is this y value? No. Because I said, what is this y value? I want y is what? Right? I need y is what? I don't have that. I got to solve this, right? So we did that yesterday. So we subtracted x. It's the square root of 1 minus x. Now it's plus minus, but which one is this one? This is the top one. Positive. This is the bottom one. Negative. So this is 1 minus square root of 1 minus x. From the strips fill the space from 0 to 1. 0 to 1. Now let's do this bottom space. Okay? What is this y value? Nope. Negative square root of 1 minus x. Right? Because it's the bottom half of the parabola. So down here on the bottom half of the parabola, y is negative square root 1 minus x, right? When I say, what is this y value? It says it right there, what y is, what y equals. What is this y value? -1. So it's that. And then dy, and the strips fill this space from -1 to 0. The strips fill the space from -1 to 0. Now, you're going to get the same answer for both of those, but I didn't care about that. I mean, the fact that I know you guys are looking at it saying, well, this area is the same as this area because of symmetry, right? So once I find this, I can just write it down. But that's not the point. The point is being able to set up these integrals. That's what we want to be able to do, right? Because we're going to do a lot of problems where you're not going to be able to do that with symmetry, right? You've got to know how to set up these integrals, so we've got to work on that. All right, this last one. Yeah, it's just a triangle. You could figure out that area without using calculus. Yes, question.
On the second one, is there supposed to be vertical lines? Shouldn't it be from 0 to +1?
The strips, oh yeah, good catch. The strip, what did I do? Oh, I drew horizontal lines.
And then try to do it with lines.
That was dumb. Thank you for catching. 0 to 1. Okay, now on this last one. See, I even need practice on doing that. It's a good thing I did that. All right, so on this one, what is this y? 1 minus, what is this y? Aha, that's the one where we've got to solve that. What is that y? That y is x minus 2. That y is x minus 2. So quantity, x minus 2. Now, could you simplify that? Sure. You can simplify that before you type it in, but a lot of times I don't, just because I want to screw it up, right? If I simplify it and do it wrong, forget to distribute the negative or something, put it in my calculator and get the wrong answer. So a lot of times I just go ahead and just leave it like that. I just type it in just like that, even though I could simplify it. And then these strips fill the space from 1 to 3. So you find all 3 of those, you add them up, and 8/3. 2 2/3. 8/3, 2 2/3 is what the book says here. Okay, now I've got 17. Now, do we have some other ones in between there, though?
We had 10.
Any problem on 10? You want to talk about 10? This was more about what we've already been talking about quite a bit, which is the units, right? So this should seem fairly familiar. So let's just quickly go over that. So if the integral is the eastward distance, okay, so they give that as an example. So F is the eastward velocity, so the integral will be the net. Notice the word net, eastward distance, okay? So if F is the upward velocity, what's the integral? If F was the eastward velocity, then the integral is the net eastward distance traveled, right? So if it's upward velocity, what's the integral? Net upward distance traveled, okay? If it's the upward acceleration, which would be like an F double prime, right? You do the integral, so if it's acceleration, then what's the integral?
Velocity.
Net velocity, right? Net velocity, or actually probably best to say net amount of velocity, right? Accumulation of velocity, okay, or something like that. Okay, and then net flow, there's the rate of flow in liters per minute, so the integral would be the net liters, the net amount of water, the net change in water in the tank. And then if F is the slope, then the integral would be, that's interesting, that'd be F prime, be the net change in what? The function F, right, or big F, or whatever, be the net change in the function. In other words, if F prime is the slope, okay, well, I mean, think of a simple example right here. Let's say F prime is 2x, okay, dx. Well, don't even do that. Don't even put something in there. Just put F prime. Let's just put F prime in. If it's the slope, let's call it F prime. Then according to fundamental theorem part 2, wouldn't that just be F of B minus F of A? Which is what? That's it, just the net change in F. Here's F of A, here's F of B, it's F of B minus F of A. It's how far upward, right, the function went. It's just the net change, okay? And that's something that's worthy of just memorization. Really, it summarizes all of this. It is this statement right here. The integral of rate of change is equal to the net amount of change. Okay? If it's negative, it means it went down, right? Like sand in the bin, right? It went down. That's negative. It's the net amount of change. So if the function inside there's the rate of change, it's the net amount change. So if the slope, which is the rate of change of F, then the integral of that would be the net amount of change of F. Okay, that is a summary right there of what the integral does. Okay, in those cases. All right, so that was 10. All right, let's look at 17. I went ahead and drawn it. Did I do this right? Is this right? Is this the right region? Okay. Now, that one said, now here you actually had to be able to understand the terminology. So it says, sketch the region bounded by the given curves and find the area. So that's the way it's going to be given to you most of the time, where you're going to be given the curves on our next quiz. You know, I won't give you the graphs. You have your calculators if you need them to be able to graph some of this stuff. Hopefully a lot of you can just graph yourself. But you need to be able to identify the proper region. Okay? You know, it's not this region up here. Right? Because it didn't say anything about the y-axis, and there's no upper bound up here. It talked about x equals 4, so you've got to get the right region. Okay? Now, in this problem, you had 17 and then 29 that were exactly the same problem, right? Except what was the difference? Horizontal, vertical. What did 17 want? Which one was 17? Vertical. If it's using x's, which is our normal way of doing it, then it's vertical. Okay? So, vertical strip would be that y minus that y. So the integral, this y value is square root of x. This y value, 0. Do you have to have the 0? No, but I like putting it because I want to always remind myself I'm doing top minus bottom. This is just a basic area function, isn't it? This is just our area under a curve, right? With area with the x-axis. So, but it's nice to know it works the same way, right? Works the same way. Now, and then it goes from what? 0 to 4? Now, let me caution you something here. Here's something where the wording does matter. Let's say you were told to find the area between the x-axis and y equals negative square root of x. That would be, and then the line x equals 4. What if the wording of the question was, find the area between the x-axis, the line x equals 4, and the curve y equals negative square root of x, which would be that region right there. Would your answer be positive or negative? What do you think? Positive. The area between, because basically what it said is the area between the two curves. That area we always want to be positive. Okay? So that, if they ask it that way, then they're saying you want the area between here and here, so you would set this up as what? Well, what's the top y value? 0. Minus, what's the bottom y value? No. Negative square root of x. From 0 to 4. That would come out a positive area. It'd actually be the same area as this. That's a different way of asking the question, right? When they ask it the area between these two curves, as opposed to the area under the curve, or just the integral. Now, I don't, that will never be confusing, I don't think, right? I don't think you'll ever get in a situation where, you'll look at that, and because when we're doing these problems, you should be thinking top minus bottom, right? And so you should set it up doing this, okay? So I can't think of ever a time where they try to trick you on that. Usually if you're going to just do a problem where you're doing this area, you're just setting up this integral. They just give you this integral and say, find this. Well, then it would be negative. Then it would come out negative. Okay? So I don't think it's really anything to worry about, but I want you to understand that when we talk about area between two curves or area of a region is a positive value as opposed to just integrals as we did it before. Okay, same exact problem now, except doing the horizontal strip. So actually I did that on the wrong one. That was 17. This one is 29. So if we're going to go this way, right, what's our x value here? 4. What's our x value here? Y squared, right? What is the x value on the parabola? It is, we're going to have to square both sides. It's x equals y squared. This x value right here is y squared. So this is what we want. This is actually number 29. That's what you want at 29. And it goes from where to where? Strips fill the space from 0 to 2. So 17, you should have that integral. 29, you should have that integral. And they should both give you the same answer of 16 thirds. 16 thirds on those two. Okay? All right. 23. You were supposed to do vertical strips. If you're going to do vertical strips on this one, what has to happen? You have to do it in two parts. Right here. This is 23. Because over here, your top y value, or the top of the strip, hits the parabola, the bottom hits the parabola, but once you get past the x-axis, the top is on the line and the bottom is on the parabola the rest of the way. You've got to divide this into two pieces. Okay? So the first piece, the top y value is what? What is this equation? It's given to you as x equals what? How's it given to you on 23?
X equals y squared minus 4.
X equals y squared minus 4, right? So what is this y value? Well, you got to solve that for y. So what would it be? Plus minus square root of x plus 4. So what is this top y value? What is this y value of this parabola? Square root x plus 4 minus this y value. Negative square root x plus 4. Turns into plus. Of course, you can just write a 2 there in front of that, or you can just type it in like that. And then the strips fill that space from so that's that half. Plus, what's this y value? What is this equation? How'd they give it to you?
Y equals 2 minus x.
2 minus x. So what is this y value right here? 2 minus x. Minus this y value. Negative square root x plus 4. dx, and the strips fill the space from 0 to 5. Add those two together, and you get 125 over 6. Is what I got in the book here, whatever that is. 125 or 20 point something. 833 or I don't know, is that 125 over 6. All right. So that's vertical strips. But this one, so number 35, this one could be done with horizontal strips, because if you stretch a horizontal strip there, it's going to hit the line on the right edge every time, and it's going to hit the parabola on the left edge every time. Now, some people say, wait a minute, it's going to hit the top half sometimes and the bottom half sometimes. Does that matter? Not when you're doing horizontal strips, right? There is no top and bottom half. Now it's x equals y squared minus 4. So what? And then this was what? Y equals 2 minus x. So we're going to have to solve that for x, right? We're going to get x equals, oh yeah, 2 minus y, so essentially the same. So x equals 2 minus y. So what is this x coordinate right here? We don't care about the y coordinate right here. We care about the x coordinates. What? 2 minus y. Minus this x coordinate. Y squared minus 4, right? In parentheses or distributive, whatever. Okay? Is it plus 4 or minus 4? Is this right? Is y squared minus 4? Okay, so in there. All right, and dy. And then the strips fill the space. You got to start down here. You always go from littler number to big number, so we start down and go up. Strips fill the space from where to where? -3 to 2. So 23, the integrals look like that. You have to have two of them. You add that up, it's 125 over 6. Number 35 would look like this, and it's 125 over 6 also. Okay? All right, and you had to find those intersection points. You had to know where they intersected and all that stuff. All right, was that it? Pretty much it? Okay, that's it. I mean, that's top minus bottom, right minus left, horizontal strips versus vertical strips to find area of a region that is not just an area under a curve. All right, let's go back to your sample 3, pull that one out, and let's take a look at that problem we didn't quite finish yesterday, number 4. So we're supposed to find this area, this blue area here. I think. What did they say? Set up but do not evaluate? Because this is a no calculator. So sometimes they will do that if it's going to be a messy kind of a function to do an antiderivative or something. They want to spend a lot of time doing that because they'll ask you your antiderivative questions in the multiple choice. So they're not that concerned about it. Okay, so they will say that so often in these problems you'll get a set up but do not evaluate because that's the key part of it. So hopefully you would look at one like this now after yesterday and you'd say, okay, do I want to use vertical or do I want to use horizontal strips? What do you think? It doesn't matter. You're going to have to split it either way. And if that's the case, I think vertical is usually better, right? Because vertical leaves everything in terms of x. Both of these functions are y equals, right? So vertical would be better because that's how we're given the functions. And so I would say you're going to split it either way. So vertical strips is how I would definitely do this. So you're going to have to split it right there, aren't you? At 2, right? That's where it's going to get split. So vertical strip over here. The top y value is what? X squared minus 3. That's the equation of that problem. Minus the line equation. What did we have? We had y equals 1, x minus a half, plus what? I can't remember. Or it's minus. Minus 2 3/4. Okay. Might be beneficial to go ahead and simplify that a little bit. X minus a half minus 2 3/4 would be x, y equals x minus, what would that be, 3 1/4? X minus 3 1/4 would actually be the line equation there. So it'd be x squared minus 3 is the parabola minus the line y value, which is x minus 3 1/4 dx, and that goes from, those strips go from where to where? Well, they end at 2. A to 2, but didn't we find A already earlier? It was 1/2, right? Now, you actually could put A there. If you've already defined something like an earlier problem, A equals 1/2, if you put A there, it'd be okay. But now you're going to, so actually it'd be okay. We don't have to evaluate it, right? They said we could stop. Oh, wait, we're not done though, right? Plus, that's just that part. Plus, okay, this y value minus that y value. So what's this y value? X minus 3 quantity squared minus the line, which is x minus 3 1/4 dx. And then these strips go from 2 to 7/2 or 3 1/2. So there would be your answer for the last part. Set up but do not evaluate the area of region R. So you can see there where you will run into this. Very common that they give you a region in the free response sections. A lot of times they give you the picture though, but you've got to find the area of that region. And then some other stuff we're going to do later in chapter 7, the volume problems. A lot of times we take that region and do stuff with it, and there's other integrals that we use as well. But the area of that region is simply that, top minus bottom or right minus left, whichever you want to do, okay? Be pretty complex to do a horizontal strip one there because you'd have, I mean, there's a little region in here you can't even see that would have horizontal strips. There'd be horizontal strips there, there'd be horizontal, I mean, it'd just be a mess to try to do horizontal strips. So vertical strips are definitely the way to go on that one, okay? You could have left your line equation like this. It would have made it a lot messier in here, which would have given you some potential for doing it wrong. You could simplify, but you don't have to. On the AP test, they do not require you to simplify this. It sure could. You could distribute that. That'd be a plus, and that it would end up being a little nicer. But you do not have to simplify algebraic expressions on the AP test, so you're good to stop right there. Okay? All right. So that is area between curves. So with that, let's get your notes out and let's go on to the other part of this section. So there's one other thing we've got to go through in section 7.1. This is, again, I stole this PowerPoint, so it says 7.4, but it's actually 7.1 for us. Okay? So, now, what's that? Yeah. I'm going to talk about that here in a little bit. Okay? So, the length of the curve, length of a curve, that's what we're talking about. So, remember, Chapter 7 is like Chapter 4. Chapter 4 was applications, uses for the derivative, different types of things. All the stuff in Chapter 4 was bound by a common thread of the fact that it used derivatives. In slope fields, we had L'Hopital's rule, we had max-min problems, we had related rates, we had all kinds of stuff that involved derivatives. Chapter 7 is applications of integrals. Okay, so everything in Chapter 7 is going to be tied together by the fact that somehow it involves doing an integral. Okay, now, integral and antiderivative are two different things. I never knew that in high school. I never knew that in college. I never knew that until I started teaching out of this book. How I missed that somewhere along the way. But antiderivatives and integrals are not the same thing, right? An antiderivative is just one way of solving a definite integral, right? And it also involves the area function and that kind of thing. So you can see where integral and antiderivative are kind of linked and tied together, but they're different things. Okay, they're two different things. But so anyway, we're talking about uses of integrals here in Chapter 7. So we just did areas between curves to find these weird areas of these different regions. Now we're going to talk about length of a curve. It makes sense that this blue curve has a certain length. And if I gave you a piece of paper with that blue curve on it and asked you to find and gave you a ruler or measuring tape or any kind of measuring device and asked you to figure out how long that is, right? And what would you do? What would be your strategy? To find the length of that. That would be a wonderful idea. Sure. Because really, is there any other way? Because a measurement is a straight measure, right? I mean, with a ruler, a tape measure, anything like that. So, very common way is get a piece of string, follow it along there, right? And then take that piece of string, straighten it, and then measure, right? That's what we would do. So, obviously, that probably doesn't work real well if I wanted to find, some length that was several miles long, a curved road or something like that, right? Probably the string method might not be the best way, right? So, is there a mathematical thing you could do? And I think, again, about engineers, we've talked about designing things, on a computer, and you have to be able to figure out these components of it. Well, the computer is going to work mathematically, right? And it's going to be based on formulas. That's why engineers learn all this stuff, because a lot of it's all computerized thing that you have to do. So if there was something I was designing and I needed to know a materials cost or something like that, I might need to know the length or of some curved surface or whatever. Is there a way mathematically we can do that? Well, what's interesting about this is, obviously, yes, the answer is yes, there is, and how it relates, how it ties in with what we've been doing already. Okay, so we just talked about how we could measure in a straight line. So one thing I could do is just measure like that, right? And I could call that delta S, S for length or string or whatever, I don't know. But a change in length, right, from there to there. Now, that's not exact, is it? That's not the exact length from those two spots, because it curves, so it's off a little bit, okay? So if we made a little triangle with that, that'd be like the hypotenuse, delta x, change in y, okay? By the Pythagorean theorem, we would have this, right? So the length of that little piece, so all I'm looking for is that length of that little piece of red. It's not the length of the string yet, or even the length of the string between those 2 points, but it's close, okay? So would you agree with all that so far? Okay, that ds, the length ds, that little red length there would equal this. Okay, now I just stuck an integral symbol on there. What does the integral symbol do?
Shows the area.
No, yeah, but what's another thing the integral symbol does?
Some
It's an adder, right? What did we just say the integral did for us? We made all those strips, right? All those strips were areas, and we wanted to add up all those areas. Well, what we're going to have here, wouldn't it make sense that I could take this little red triangle and I could have put a bunch of those along that strip, or along that curve, right? And so what I want to do is add up all those little ds lengths, right? Add up all of those little lengths, okay? The integral could be an adder for that, to add all those up. Now, what would make this red length, this red hypotenuse, more accurate?
they were littler.
They were littler, right? You see the common theme here from stuff we've done before. There were more of them. If I could add up how many of them? An infinite number of them if they got so small, right? Okay. So now, what we want to do though, is we want to make it look like an integral. We need to get that dx piece. We got to have that something. We got to have that dx. That's how an integral works, right? It's got to have that dx thing there. There's got to be some component of it that goes to nothing, right? As we have but look what's going to happen is that ds, as those get littler and littler and littler, the dx is going to go to 0, isn't it? Just like the width of our rectangle, same thing. So now we just need to do a bunch of algebra here. So we need to get this dx outside of it. Okay, so what we're going to do, now that's a little hard to follow right there, so I'm going to write down what they just did there. What they did is they said, let's take this inside of here, let's take that times dx squared over dx squared. Okay, so what they did is now and let's put this over 1. So if I had like 2/3 times 3 over 1, right? Let's don't do that. Let's do 3 over 3, right? Let's say I had 2/3 times 3 over 3. Wouldn't it be okay to go ahead and multiply the 3 there and make it 2/9 and then leave that 3 out there like that? I mean, aren't those the same thing? Aren't those both 6/9? Right? In other words, I just went ahead and multiplied the 3 there and just left that 3 set there. Right? We're going to do the same thing here. I'm going to multiply this dx squared into here. Okay, so I'm going to have a dx squared inside the parentheses here. Now, this is all inside the radical. I'm doing this. Okay, so I'm going to multiply this dx squared to the bottom, just like I did with that 3 over there. So I'm going to have a dx squared under there and a dx squared under there, right? With me? And then this dx squared here will just hang out outside there, just like this 3 did. Got it? Okay, so that's just some algebra there. So I get this. Okay, now let's simplify that a little bit. What's dx squared over dx squared? 1. What's dy squared over dx squared? Just that. And then dx squared. Now, this is hard to see here, but we got this parenthesis. We got this parenthesis times this all under the square root. So that's kind of like having square root of 3 times square root of 4 under the square root. Well, can I make that as square root of 3 times just 2 outside the square root? Right? That's something you can do without it. So what I'm going to do is I'm going to do that same thing. I'm going to leave this inside the square root, but the dx squared, I'm going to pull that out as just a dx. So this dx is now outside the square root, and that's what I wanted. For my integral, I needed there to be a dx sitting out there. So I just did a little algebra to get that to happen. Okay, so now I have that. Right now, let's finagle this. What's another way to write a fraction like 3 squared over 4 squared? Right? Isn't that the same as 3/4 squared? So dy squared over dx squared, isn't that dy over dx? What's dy over dx? Y prime. That's y prime, isn't it? That's y prime. So look at this. So the integral adding up. So what I have in here, remember what I had inside here. What I had inside here is just the length of S. That's what I had in there, is that length, that ds, that little tiny length. Okay? And the integral is now going to add up all of those lengths along that curve. We're going to let them get smaller and smaller. Then they're going, so they're straight, so I can measure them. But if I have an infinite number of them, I essentially will get the length of that curve. Okay? And so the integral is adding up all of those little pieces of length. Okay? And so we end up with this formula right here. Now, you'll see me typically I will write this. Well, let's see. I got it. Typically, you're going to see this written as the length of a curve, okay, or arc length. Sometimes it's called arc length, okay, but length of a curve is equal to the integral from a to b square root 1 plus f prime of x squared dx. Okay, the dx is not under the square root, by the way. Okay, you just have to memorize that. Just like that average value of a function, it's the integral of the function over b minus a. Same thing here. You just have to memorize the length of a curve is the integral of, and now the curve we're talking about, let's say that this is the length of f of x, right? That's what we're talking about. So the length of some curve f of x, you do the integral of square root of 1 plus f prime quantity squared, just the f prime is squared, not the 1. And then you're just going to type that in your calculator to get the answer.
So is there a benefit of doing this equation rather than doing it like geometrically?
How would you do it geometrically?
Well, like, you know, in geometry when you solve arc length.
But in geometry, the arc length is what?
I don't know.
What is the arc? The formula for arc length in geometry is only for a circle. That's only for a portion of a circle. This is for a curve on a parabola, on a, you know, x cubed, on anything. Yeah, the arc length formula for geometry is only a portion of a circle, is all that is. Yeah, I think, what is it? It's like S equals r theta in radians. I think in trig you'd add that. That's the length of arc, but that's only around the circle. It's only around the circle. Yeah. So this is just much more useful. Yeah, this is the length of any curve. But that's why it's kind of confusing. That's why I like to say length of a curve instead of arc length, because when you say arc, you think of a part of a circle. So that's why I'd rather not use the term arc length. Okay? So here's an example. So let's go ahead and put this one down. So let's say, so the question would be, find the length, right? Find the length of y from 0 to 3. That would be the question. Find the length of the curve y equals negative x squared plus 9 from 0 to 3. You don't need a picture unless they tell you to draw a picture, but they went ahead and drawn it. They drew its upside down parabola, shifted up 9 from 0 to 3. We want to find how long this piece of curve is. That's all we're asking. How long? So it doesn't have anything to do with area at all, but it's an integral. Why? Because an integral is an atom. And an integral is adding up these infinite bits of stuff. And those infinite bits of stuff can be things other than area. It's a great example to start with. We're adding up infinite rectangle areas, but the integral can just add up anything, because integral comes from sigma. Sigma comes from adding infinite number of things, or integral comes from adding infinite number of things. So what are we going to have? Integral from 0 to 3. I mean, these are really pretty easy to do. I mean, 1 plus what? Negative. That's it. I mean, how easy can it be? Right? Easy, easy. All you need is the derivative of the function, the derivative of the curve that you're trying to find the length of, which in this case would be negative 2x. You square it, and you can type it in just like that. You can leave it like that. Now, of course, we know that would turn into 1 plus. We know that would simplify, which is fine if you want to. It would simplify into that. Okay? Now, there is no nice antiderivative for that. You know, I think they go on to talk about it here. Okay? They do the derivative. They write down the formula. There it is right there, which would be that. And then they say, you know, this is not fit a formula. It doesn't have an antiderivative, so we can plug it into our Inspire and get that right there. 9.747. Makes sense because this thing is mostly going down. It's 9 tall, so it's got to be longer than 9 because it's going out a little bit. So it's longer than 9, but how long? So that seems to be reasonable. It would be about that long. Okay? All right. Oh, and then they went ahead and did it. What if we just did one line, one curve, right? What if we just did that red dotted line? Comes out to be square root of 90, which is 9.49. Well, we can tell the blue line's a little longer than that. Okay? So that seems reasonable. So that was a check. Okay, they talked about, oh yeah, let the calculator do the derivative. Now this is interesting. They go through here. I never do this. We talked about defining a function. Define f of x. You know, you could do that. What they do, and this is also something you can do, store it as a variable. So what they did is they hit negative x squared plus 9 and hit control store in y, and then they stored that in the variable y. I don't like storing things in variables. Like you store something in x, and then all of a sudden you want to use x as a variable later. You've got to be sure to go back and clear it out. And they talk about that here. So it says you must delete the variable y when you're done. And so I just would rather not even do that. You go into the menu under actions, there's a choice 4. It says clear the A through Z variables, and it'll just clear out any of the variables. So if you're ever getting weird answers, like if you ask it to do the derivative of x squared, and it doesn't give you 2x, it gives you like a number, well, that means something has been stored in the x variable. So you go into your menu, just clear out the A through Z variables, and take care of that. So that's something I would typically do. Now this is a circle, right? This one is a circle. So now we can actually check it with our geometry. Okay, so on this one, it's a top half of the circle, so we would want to solve it for y first. Okay, so now, if we're going to do our formula, and they didn't work it out, but we would just want to do the derivative. But again, if I'm giving you your calculator to use, you can just let the calculator do the derivative of that, right? I mean, it'd be 1 minus x squared to the 1/2 power, so you have to do a chain rule, bring the 1/2 down in front, times the derivative inside, the whole thing, right? But you can let the calculator do that derivative. And then you put it into this formula, and it gives you pi. Well, does that make sense? That's the unit circle, right? What's the circumference of a circle? 2 pi r. If the radius is 1, the circumference is 2 pi, right? So the length of the curve would be the circumference all the way around would be 2 pi, so half a circle should be pi. So if you do that problem, you type it in, you will get pi as the answer. So it checks with our geometric, what we know about geometric. Okay? And you get a smiley face. All right. So you know I didn't make that. Yeah, I won't go into that. Solving for that. So we don't. That's good. All right, that's it. I mean, that's all I've got with that particular thing. So let's talk about the assignment here. So on your chapter 7. Assignment sheet, okay. Oh, is that a new LH packet? That might be. So I think I've got to give you, I think I might. I don't think that's one of the LH packets we already had. Might be. It's not. Okay, I'll have to print that off for you. All right, so there's our assignment for tomorrow. Now, you're asking about the packets. Okay, so let's get these 2 packets out. We'll change the assignment a little bit here. These are going to be, so this is for tomorrow. Okay, now I've got a track meet. I'm going to be in and out. Tomorrow's a JV track meet down here on our track. I'll be in and out. Tomorrow's going to be a lot of work time on these things. So for tomorrow, we're going to do those 2 right there. Okay. Due on Monday is going to be sample 3. Okay. And your motion packet, I want you to look for that. Let's pull that out. Motion packet.
What's that?
It's a packet about motion. I don't know what else to tell you. Yes, you have it. Let me go to somebody organized here.
Not me.
That way, Jamie, that boy.
Jamie.
See, you guys work.
Jamie, why'd you find it?
That's not it. Way to go, Jamie. Okay, gotta go to somebody else. Caleb, all right. It looks a lot like that, though. Okay? It says worksheet 1, what you need to know about motion along the x-axis.
What?
Do, I
Oh.
didn't see that.
Well, hopefully you can find it because we've done a lot of it already.
Oh no. That's gonna suck.
Here it is.
Why did we get that?
Oh.
It was?
It was a long time ago.
Well, how in the locker that
You can go look if you want. I don't know, 2015. Oh, I think it's since we've had it since. It's like beginning of. No, that's not the one that's about tables. I the one
Yeah, it
that's
was
tabular data.
Go back to my old.
Might be in your old folder. I don't know. No, we've done it since.
What does it say on the front?
Worksheet 1. What do you need to know about motion? It's the only packet I've ever given you on the front page. The title has the word motion. So it'll be easy.
Oh my gosh. Oh my gosh.
Got line the Ranger, good.
Yep, but I don't know if I have motion. Oh.
Oh, now can I go?
Is that it?
Let me try lock.
Yes, you may. Go look.
Done.
Well, good. I'm glad I gave you a few days to look.
Hey, I found it. Wow. That's unlikely.
It usually happens. Everybody freaks out.
Look, I never actually happened, so that was like crazy.
Okay?
Oh, it was that. It was old.
So we had worked up. We had done about half of it. Maybe not quite half. We did all the
We
ones
did through 16.
through page 16. It was a short little quiz. So basically by Monday, so again, you've got all day tomorrow. I do have a couple other things that I will have, the sub will have up there, and I'll put them up here before the period ends. They will not be handed in yet, but there'll be things you'll want to do to stay caught up with things you'll want to do on some of the free response packets that I've already given. Okay, the 2000, what we decided the other day, 2012 and 2015 packets. Those will not be handed in. Those are the two that will be handed in on Monday. Okay, so this motion packet will be finish the motion packet. Okay, now I will tell you, this was Kate. Okay, I will tell you two things that will be important in the motion packet, and that is, and well, you'll tell me here. What is the integral of velocity? We just had it in problem number 10, actually. We got to write more than distance.
Net distance.
There you go. Net distance
Travel.
traveled between A and B. Okay? Now, that, of course, is velocity. What is that? When we do the absolute value velocity. Speed. And that is total distance. Okay? On the motion packet, there, and the last part of the motion packet is about is integrals with motion. The first part that we already did was about using derivatives and stuff like that. Now integrals will become involved. Okay, but you can wait on that. You can work on that tomorrow. Okay, for now, I would say let's work on this. I'm gonna go ahead, it's gonna be some length of curve, the book stuff's gonna be length of curve stuff, and then this is gonna be some more, areas of regions, top minus bottom, right minus left, and I'm gonna print that out. And I'll get that to you before the period ends. Okay, alright, so the rest of the time's yours to work, and then I'll put the other stuff, because a couple people told me they'd be gone tomorrow. So also that you'll work on tomorrow, there'll be some problems in the 2012 and the 2015 free response that we'll be working on, but those are not due. These are the two that are due on Monday. So that's the first priority. And then there'll be some things here, and I'll put up the specific problems I want you to have on that. Okay? All right. So, the rest of the time you can go ahead and, I would say let's work on this right now.